Newtonian mechanics. Right, so if we do have time tonight, we'll do some questions as well. So section 2.1 deals with transforming Newton's second law. Right, so as we looked at before, that force is given by the time rate of change of momentum. And this is essentially m multiplied by acceleration, right? This equation here, this is ma, right? The position vector r, that gives our x, y, z coordinates, and the velocity v. This is given by the time rate of change of the position vector, and then acceleration, which is equal to the time rate of change of velocity. And this here means that we're looking at d dt of v, and v was equal to dr dt. So as you can note here, that this is d squared r dt squared. So this is the acceleration term, and this is equal to m multiplied by r double prime. So the r prime here, well, r double dot, sorry, not prime. So this here can also be represented as r dot, which means that that's the first derivative of the position vector. And for r double dot, that's the second derivative of the position vector, which gives you acceleration. So once you see that dot, this kind of a notation, just know that your r is given as a function of time. Right, so you will define the r here in terms of t as a function of time. So as an example here, we're given Newton's second law to two-dimensional polar coordinates. So you were introduced to polar coordinates in first year math, right, in algebra. In two-dimensional coordinates, Cartesian coordinates, we write Newton's second law for a single particle of mass ms. So this is fx is equal to m multiplied by x double dot, and fy is equal to my double dot. So this is the acceleration, but in the x direction, and acceleration in the y direction. All right, so just quickly, with x double dot, that means that we look at the second derivative of x, right? And then for y double dot, that's going to follow the same procedure. So essentially, we have x, which is equal to r cosine theta, right? This is a definition of x for polar coordinates. So you're going to have x dot, which is minus, we can start with r. So we'll treat r and theta as two independent variables. So that means that we'll have cosine theta minus r sine theta dot. Right, and so essentially what's happening here is that with the first one makes sense, right? When you differentiate this here, where you're treating r as your independent variable, that goes to 1, meaning that you're left with cos theta. And then this one here, when you differentiate, so when you differentiate that, we use the chain rule. We differentiate the outer function first, which is cos, and then it becomes minus sine, and then you keep the inner function as is, and then from there you differentiate the inner function. So it's theta dot. So meaning that our x dot here as a function of r and theta, this is cosine theta minus r theta dot sine theta. Right, so that gives you the velocity in the x direction as a function of r and theta. Right, and then to get to acceleration, you can do the double derivative of that. Right, and just a minute. So we said this is x. Right, we can apply the chain rule to the function as also. When we differentiate the r here, so instead of going to 1, it's going to be r dot. Let's just correct that. And then x double dot, you can you do this one first, meaning that it's now going to be r double dot. So what we're using are the product plus chain rules. And from there, you can write fy as a function of r theta as m, which is equal to. So this is basically the acceleration term, ay. Is everybody happy with this? Are there any questions here? All right, no questions. And we can generalize components of force in the r and theta directions. So that gives us, so consider the cosine theta here, sine theta, and fx and fy. Right, so this gives us the x component of force in the x direction and then the y component of force in the y direction. So here we have QR, which is ER dotted with F. Right, and here we're given Q theta. Right, so this is E theta dotted with F. And that gives us those terms. And so continuing with the transformation of Newton's second law into two-dimensional polar coordinates. So given our rxy, right, you can write this as the polar coordinate equivalent. So meaning that this is going to be r cosine theta, r sine theta, and this is equal to r hat. And the derivatives, you're already familiar with that. So d r hat dt, that means that this is d dt of cosine theta sine theta. Like this r hat here, that r hat expression. And then you can do the derivatives of that. And then this is theta dot multiplied by minus sine theta, cosine theta. And this is equal to theta dot and theta hat given by that. And our d theta hat dt, this is d dt of this theta hat term here. So this is r hat. This is theta hat. And you can do the derivative of that. And you end up with minus theta dot and r hat. And r hat was set t. So this is theta hat. All right, as a simple 5-minute exercise, right? So given all right, because this is what we're going to rely on the most, and it's quite important that you understand it. So given x, which is r cosine theta, Please find x double dot, and given y is equal to r sine theta, please find y double dot. So this shouldn't take you more than 5 minutes. So the reason that I'm giving you this short exercise is that sometimes you may look at it and think that you know how the steps work, that you can do it, but then when you now have to actually do it, you may struggle with it. So just take that, and then when you are through with it, please let me know. So remember, chain rule plus product rule. That's what we rely on. So when you go from x to x double dot, that means that you also have to give the x dot term, which is in between. And from there, you can go from x dot to x double dot, or from y dot to y double dot. Is everybody done? All right, perfect. Hopefully everybody did get a chance to see what I meant by you need to be able to actually put it down on paper and see that you can get it. So with x dot, that is going to be r dot cosine theta minus r sine theta dot x double dot. That's going to be r double dot cosine theta minus r dot sine theta double dot, and minus r dot sine theta dot sine theta multiplied by theta dot minus r cosine theta dot squared minus r sine theta double dot, like that. And that will be your r double dot all right, so these two expressions here are the same, meaning that you can add them up to give you that minus 2r theta dot sine theta, like that. R theta r dot. Hopefully that's what everybody got. And then you must have done the same thing for y double dot. So continuing. So it's nothing too hectic. You just have to understand what it is you're doing. And here we have r double dot, which is d squared dt squared r multiplied by r hat. And so d dt. All right, so you can differentiate that once, right? That leaves you with d dt. So that means that it's going to be r dot multiplied by r hat according to the product rule, plus r multiplied by the derivative of r hat. Right, and our definition for r hat here, we define that to be cosine theta sine theta. And that's r theta dot multiplied by theta hat. And the second derivative of this here, this is going to be r double dot r hat plus 2 r dot theta dot r hat, and then plus r theta double dot theta hat minus r theta dot squared r hat. So if you find this confusing, you can just use the r hat expression in its entirety and then see how it actually just gets back to what we have here. So to just give you a quick example, so if we do d dt of r hat, d dt r hat was cosine theta sine theta. So this is minus theta dot sine theta, theta dot cosine theta, and this is minus plus. Let's look at it as plus theta dot minus sine theta cosine theta, and minus sine theta cosine theta, that is theta head. So what we're looking at there is theta dot multiplied by theta head, and that's that. Those are the terms there, and that is going to apply throughout. So if you ever feeling unsure of that, you can just refer back to the original designations. Does anybody have any questions so far? All right, no questions. And since that's the definition of acceleration, our R double dot, right, that means that that's M multiplied by R double dot. And what we have here, our sum of forces is equal to mass multiplied by acceleration. And this is R double dot. So you just sub in these terms in there. So if you take out M here as the common factor, this just goes back to how it was before. Plus R theta double dot plus R theta dot like that. And those represent our radial and tangential components. And so we note here that since unit vectors are orthonormal in polar coordinates, that the first inner product is going to be 1. And the second is 0. So r hat dotted with r hat, that's going to give us an answer of 1. But if we do r hat dotted with theta hat, that is going to give us a value of 0. So meaning that this is the only term that remains for QR. And then for Q theta, what remains is M multiplied by R theta double dot minus R theta dot squared multiplied by R. So we notice that the curvature has appeared in the shape of the metric coefficient R. And Q theta is not the component. So meaning that we take distance and multiply that by length to get the same units. We remark that the component of force QR indicates along R indicates along R hat indicates that there's an associated acceleration along R hat that is a function of R double dot R and theta dot. So you note all of that from the equation. Most notably, if we enforce that R is a constant, then R dot R double dot those all go to zero. However, the component of acceleration R hat does not vanish. Instead, it's going to reduce to minus R theta dot squared. Right, so this is what will go away, but this here, that will remain. And this suggests a resultant along minus R hat with a magnitude that is proportional to the square of the angular rate of change. With that being theta dot and distance r from the center of the coordinate system. This centripetal, which is center seeking acceleration, corresponds the fictitious force that is not apparent in the xy coordinate system. So such fictitious forces are a common feature of the curvilinear coordinate descriptions of mechanical systems. So our results here with m multiplied by r double dot, that's equal to qr plus m r theta dot all squared, and m theta m multiplied by theta double dot, that's 1 over r squared q theta minus 2m multiplied by r dot theta dot divided by r. So what we were doing was that we went from Newton's second law of motion to polar coordinates. And we got our FR and F theta. These are the physical components of force. Does anybody have any questions here? So, yeah.
I hope you're good. I have a question on what's the reason we're changing them from Newton's second law to polar coordinates? Is it because when you make it like easier to work with, or what? What's the main reason behind it?
All right, great question. So the radial and tangential components are mostly useful when we're looking at circular motion. Right, so if we have some kind of a path that looks like that, let's say it's a vehicle which is turning a corner. There's going to be that center right there in there. The limitation of Newton's second law in applied to the xy coordinate system is that the math will be quite complex for such a system. When we use polar coordinates, right? When we use Newton's second law but applied to polar coordinates, what we note is that we're going to have a tangential component which is tangent to that path, and one which is radial. Right, so that one extends to the center, to the origin of that corner. So we'll take examples where we demonstrate that how that works, but the main application is that the math is applied to circular motion. Does that make sense?
Yes, thank you so much.
All right. And now we want to include phi. So meaning that instead of those 2 dimensions, now extending our study to 3 dimensions. So we define our rho hat here to be sine theta, cosine phi, sine theta, sine phi, cosine theta. So this is the if I'm not mistaken, the coordinates of a sphere. And our theta hat here, this is cosine theta, cosine theta, sine phi minus theta. And phi hat itself is minus sine phi cosine phi 0. So what you usually have is that you have R right, so you have X, Y, and Z harmony, and this will be your R cosine theta, R sine theta, and this will simply be your Z like that. And now we extend, well, 1. Right, to now account for, let's call this K theta in phi. Right, the simplest you could have it is X, Y, and then the Z component being 0. And now we add the cosine phi, sine phi. And cosine theta. So given some kind of a sphere, you need to account for any rotation that you might have along this plane here. That will be theta event. Any angles that you can have on the surface of that sphere, you want to account for that using phi. And then the derivatives, we've looked at that. So d rho hat dt, that is equal to theta dot multiplied by theta hat plus phi dot sine theta phi hat. And you can also do d theta hat dt, that's equal to that. And then d phi hat dt. And we're going to come back to these results to use them. So here we've given our position vector, which is r multiplied by rho hat. So r dot here, meaning that that's the derivative of that. You're going to apply the product rule. So you'll have r dot multiplied by rho hat plus r multiplied by rho hat dot, and then when it comes to playing around with the maths, I'm going to leave that to you as homework. Just practice and see if you actually do get the same expressions. So once again, we're going to have components of force in the theta direction as well as the phi direction. And so we require a good motivation for all this effort, right? So our motivation might stem from the motion of the system being constrained to take place on a sphere or a cone. In such cases, the equations above might prove useful. Nevertheless, if we need to transform Newton's second law to some new coordinate system for each problem to solve, then we're going to be spending a lot of time transforming equations that could be better spent elsewhere. We notice that our problems come from the fact that Newton's second law, or those laws, are not transformation invariant. they have different forms in different coordinate systems. The equations of motion will meet later will be transformation invariant and hence much more elegant, those being Lagrangian equations. Right, so for this chapter here, what you need to understand is the transformation. And also, if you have any question, you can feel free to message me about that as well. That is acceptable. But before we continue, let's take a 5-minute break. And then when we come back, we'll complete the rest of the chapter. We'll come back at 21:16 p.m. See you then. Can everybody still hear me? All right, perfect. 1 second. I thought we were still gonna. There was little work after this, but it seems that there's still a bit more we have to do. So instead of just cramping everything into one lesson, we're going to end off with section 2.2, and we'll continue from section 2.3 constraints in the next one. So when it comes to these ones here, just play around with the math and see if you do get the equations correctly. Right, so section, we're now going to consider oscillatory motion. So this is motion that oscillates. Now we'll consider related ideas of circular motion. This is given here in figure 2.1. And the motion of a simple pendulum, which is given here. We first consider an object constrained to move in a circle. In polar coordinates, this means that r is constant. Right, so if it moves in a circle, remember that our x squared plus that's x squared plus y squared, which is equal to 0 for a circle centered at the origin with a constant radius r. If this is our motion and our object which is constrained to move in that circle, it's always going to have a radius r which is constant. So that will mean that r dot is equal to r double dot, which is equal to 0. The velocity in polar coordinates is given by this equation here, where we have r dot multiplied by r hat plus r theta dot theta hat. And the acceleration, as seen before, is r double dot minus r theta dot squared r hat plus 2r dot theta dot plus r theta double dot multiplied by theta hat. And if these terms here, r dot and r double dot are equal to 0, the equation can be simplified by two equations. So meaning that this can be cancelled out, that can be cancelled out, this can be cancelled out. And this is what remains of our velocity. So this is our linear velocity. And so since the velocity is tangential and of magnitude r theta dot, and the acceleration has both a tangential and radial component. As we've shown that before. So if this is the path of the motion and this is the center, if the acceleration has those two components, that means that we'll have that tangential component as well as the radial component. Velocity r multiplied by omega, that's tangential to the circle. So our linear velocity, this is equal to omega r. This is the angular velocity. multiplied by the radius. So if you wanted to work out what the linear velocity of the particle is at this point here, or at this point, that will be velocity, this linear velocity. And if you're given its angular velocity, omega, and you know the radius of that circle, you can work out what v is. And the radial component of acceleration is r omega squared. And that's the acceleration component that points inwards. And the acceleration can also be written in terms of velocity. Right, so in the place of omega, we can sub in that v over r. Right, so if acceleration has that component, so meaning that's what we need to make the subject of this equation. So that's our omega r. So meaning that this is going to be v over r all squared. But this here is going to cancel out 1r, leaving v squared over r. And the minus sign is due to the fact that this acceleration is pointing towards the center, towards the origin. So it's negative in that direction, and then if it was pointing in that direction, it would be positive. So that's how the radial direction is set up. It's set up in such a way that what points inwards is negative and what points outwards is positive. So now we're going to consider a pendulum comprising a bulb of mass m, which is attached at the end of a rigid, massless, inextensible rod of length r, L. And this is free to swing from anchor point without the influence of any outside agent, and will swing smoothly on a circle about this anchor point. So there's a force initially that accelerates, that imparts motion to the system, but from there, that force is removed from the system, from the analysis, and we look at the motion of the pendulum under its own momentum. And so note here that the path will look something of this nature here. So you're going to have a component that's radial as well as tangential. So our FR can be written in that manner, and then F theta. So we notice that we constrain to fix the radial component of the bulb to R is equal to L. So that will mean that R dot is equal to R double dot, which is equal to 0. The value of R is not changing. So that means that when we take the derivative of that value R, it's going to go to 0. Are there any questions here? All right, no questions. And according to the coordinates in the figure, the vector R hat points diagonally downwards, away from the anchor point at O. And for the pendulum in this configuration, the weight of the bulb acts in the negative y direction. and the tension starts in the negative R direction. So remember, whatever points towards the center of the pivot point or the origin, right, that's going to be negative. You've seen this weight equation before, so that's minus mg, and we've now attached direction to it, and this is tension, so minus t. Also attach the direction to that, and the projection of the weight in the direction, in the r hat direction, this is given by r hat dotted with w, right? So it's simply the component of weight in the r hat direction, which is mg cosine theta. So you can also do that with some simple geometry. So that's mg cosine theta. Theta is the angle between r hat and minus y hat, that theta day. It is clear that this should be the case since theta is the angle between the quarter of the pendulum directed along r hat and the line running parallel to the y-axis. Similarly, the angle between the weight and r hat is also theta. In contrast, the theta head direction as measured in m is orthogonal to r hat. So that relationship, always expect that to be true. R hat and theta hat, those are always going to be perpendicular to each other, those two directions. So as you can see here, that in all drawings I've made, these two components are perpendicular to each other, always going to be orthogonal. And the projection of the weight in the theta direction, that is going to be theta dotted with w. That's theta mg minus y hat, and you end up with minus mg sine theta. What the angle between the positive theta direction and the minus y hat direction is theta plus pi by 2. Does anybody have any questions here?
Yes, I do. I don't understand how we got to that. How we got to the minus mg sine theta. Can you please explain the process?
All right, so this is the reduction angle. How we go from here to there. So what you might struggle with here is the perhaps theta plus pi by 2. But this here to go from here to there, that's reduction formula. Does that ring a bell?
Yes, it does. It does.
All right, so with the angle here, we consider the projection of the weight W in this direction. So we have this angle pi. So essentially, we consider this theta plus the 90 degrees there as theta plus pi by 2. So that's how we come to this angle there. Are you happy with this?
I'm very happy. Thank you.
And in contrast here, we consider tension force directed along minus r hat, meaning that it points towards here. So this is not going to have any theta hat component since they already parallel to each other. And our FR, we consider our R hat dotted with W plus R hat dotted with T. And that's simply mg cosine theta minus T. Right, so we had looked at the weight component in the R hat direction, which was this value. And then tension in the R hat direction, that's simply the minus T. Right, that's T here. So there's not going to be any theta angle since they parallel to each other. This is T and then this is R hat. And our F theta, right, so the weight component in the theta hat direction, that's going to be, that's minus mg sine theta, while this is 0. So we had placed a restriction to say that R is equal to L, and that's a constant value. And consequently, R dot is equal to R double dot, which is equal to 0. And this implies that our radial component of force that is equal to 0 when R is equal to L is fixed. That will mean that F theta is what's responsible for the movement of that pendulum. And T is equal to our M L theta squared plus G cosine theta, and our M theta double dot that is equal to minus mg divided by L sine theta. Right, then the R component gives us the required value of tension, the force of constraint, and the theta component gives us the equation of motion. And this doesn't have any mass terms in it, right? So it's independent of mass. So whether we choose a 1 kilogram bob or a 2,000 kilogram bob, the motion executed by the pendulum, provided the rod band, will be exactly the same. This differential equation itself is difficult to solve exactly. We first consider our approximations valid in certain regimes. In particular, we ask how the system might behave when theta is small near equilibrium. And we use the Taylor series expansion of sine theta for that. And sine theta, that's expressed as theta minus theta cubed divided by 3 factorial plus all the way to our last term. So we chose sine theta here because we used the approximation that if we have a small angle, then our sine theta is going to be approximately equal to theta. And and also the fact that it's present here in the equation, so it makes much more sense to use the Taylor series expansion for sine. So once we're able to take that to theta, now it becomes much easier to solve. And now theta as a function of time becomes this equation where A and B are determined by any given initial conditions. So equivalently, our theta as a function of time, this is equal to R cosine square root of g over L t plus phi, where R and phi are determined by those given initial conditions once again. And from this last expression, you can clearly see that for small angles, there are a simple harmonic motion of amplitude R and phase offset phi is executed. That was a lot of theory. So instead of continuing with section 2.2, what we're going to be doing now is questions. We'll resolve this section for after questions. Does anybody have any questions for section 2.1?